This video will discuss heat as a physics term, not as used in everyday language, but has a specific uh, physics meaning, and there's a specific heat that'll come up later. But we want to talk about energy and temperature change and change of phase. Those are our main topics for this video. And you have experience with this, with the change of seasons. If you live at a location like Nebraska that can have change of seasons, and you have to be ready to put on a coat to minimize your energy loss due to wind carrying off high energy molecules from around your body, and to prevent radiation, not nuclear radiation, but light, infrared radiation from cooling down your body. The Earth has a molten core. There's a resupply of energy in our core from radioactive decay of isotopes. It's not all the original energy is when the Earth formed, but those are some examples of this concept of different temperatures and energy in motion, moving from one place to another. There's energy moving from the core of the Earth to the surface. That is a heat. And heat is the transfer of energy due to a difference in temperature. So you should memorize this definition. Heat is energy transferred due to a difference in temperature. And heat will have units of joules, the same units we use for kinetic energy or work. And you just have to get used to the fact that it's energy transferred. So what heat can do, an object that is receiving energy could have its temperature go up, or it might melt or go into the vapor state. So that energy can accomplish some work on the object. And if we extract heat from extract energy from some object, we can lower its temperature, or we could change the phase back to a solid if it was liquid. But we're going to talk about energy going into a system or out of a system and calculate what happens to the system as a result. That's the theme here. So, soft drink can, ice cube, they can have different temperatures when they're apart. And this is a little bit simplified diagram, but if we put them in a big beaker side by side, then eventually they'll reach the same temperature. The ice, of course, is going to melt, but we can have the same temperature, equilibrium temperature, if we would maintain this system here in a more of a restricted environment where the water can't flow away. So that can happen. So Joule, in the 1800s, born in 1818 and did his work in the middle of the 1800s, investigated in a controlled way the delivery of energy to water by letting masses drop a known height. So mgh, there's a certain potential energy that the mass releases, and we have stirrers here stirring up the water and then recording the temperature of that water. So Joule did experiments that gave us this foundation that work is involved, energy transfer is involved, the energy transfer of the gravitational potential energy into energy inside the liquid. And again, you need to remind yourself, temperature is a measure of the average kinetic energy. Temperature is a measure of the average kinetic energy. An old unit of working with these calculations is the calorie, an energy unit called the calorie. This is not equal to the food calorie. The food calorie is 1,000 times bigger than the physics calorie, but there is a unit of energy called the calorie, and we may or may not show you some calculations with that. But the joule is the standard unit of energy in this chapter, and many times we'll use kilojoules because the energies are going to be larger than just the joule range. But joules or kilojoules, both of those are acceptable as good units to use for the energy. So here's a little illustration of the concepts that would be involved here. Here we have an object, a mass m. It undergoes a change of temperature delta T when we deliver Q units of energy. What if we deliver 2Q units of energy and the object maintains its phase? So it's solid here, it's solid over here. Is it reasonable to you if twice as much energy comes in, there'll be twice as much change in temperature? It is true. It is true. There's a proportionality. Q and delta T are proportional to each other. As long as the phase is constant, we stay solid, or if we would stay liquid in the two situations, as long as the phase does not change, then we can do this proportionality. The change in temperature is related to how much energy comes in or how much energy is extracted from the object. And delta T can be positive or delta T can be negative. Delta T is positive if the temperature is increasing. Delta T is negative if the temperature is decreasing. Q is positive if energy is going into the object. Q is negative if energy is coming out of the object. Second example here, if we change the mass of the system. So you can see the delta T's are prescribed to be constant, same value. Now, if we double the mass, it's going to take twice as much energy to achieve the same delta T as the object that has 1m units of mass. And then if we would take a look at water versus copper, if we feed in a certain amount of energy into the copper, we'll get a delta T value. It turns out that water is very stable for its temperature, and we have to deliver almost 11 times more energy to the same mass of water to achieve the same temperature change that was observed in the copper. So the metals here, this copper is an example. We deliver 1 Q to it, we get, and the mass is 1 unit, we get a certain temperature change delta T. To get the same temperature change in the same mass of water, we have to deliver a lot more energy, So it is actually good that your body is basically water. It gives you a protection against your temperature changing very much in the summer or the winter. As energy comes into your body or if energy is leaving your body temperature slowly changes in those situations. If you want to go on a vacation in January, perhaps you go to Hawaii that's surrounded by water, or the coast of Florida that has water near it. And those bodies of water moderate the local weather and cause the temperature changes to be smaller than in, say, Nebraska. Here's a truck going downhill. The brakes are on, and we can see that some temperature changes going on here. The brake pad material is smoldering as it's receiving energy, this work done with friction, raising the temperature of the brake system to the point where it's smoking. An icicle here with warm air blowing past it will raise the temperature and lead to a phase change going from solid to liquid. So this phase change situation, starting as a solid, we've got significant bonds between neighboring molecules or atoms. If we deliver energy to this, then we can break those bonds and we get a liquid. If we deliver more energy, we can separate the particles farther and get a gas in that situation, or a vapor. But in this process, when we're delivering this energy, let's deliver energy to this cube here, as long as we've got some solid material left, the solid and the liquid here will have the same temperature. There is no temperature change. So, say example, ice. So we have ice at 0 degrees Celsius. As we deliver energy to this system, we'll get a situation where we have some ice and some water, but it'll all be at 0 degrees Celsius. And when we get all water at 0 degrees Celsius, then we'll start to change the temperature of the water. But during a phase change, the temperature is constant. That's something you need to memorize. During a phase change, the temperature is constant. So if we're going from solid to liquid, or if we're going from liquid to vapor, the temperature is a constant. So why is it that a recipe can say cook the green beans, boil the green beans for 5 minutes, and the recipe will work and give you well-cooked green beans? I don't know if 5 minutes is appropriate, but the reason is when water boils, when it reaches that boiling point on the stove, the temperature doesn't keep going up. It's not going to be like an oven, go to 200 Celsius or 300 Celsius. The boiling at sea level occurs at 100 degrees Celsius, and slight change as you go to higher elevations to a lower boiling point temperature. But in the realm of cooking, it's acceptable to have a little variation. But basically, the recipe knows that there's a fixed temperature for boiling and gives the correct result. Well, here is a chart that describes how the temperature changes, a graph of temperature changes, given the energy going into the system per mass. And they're using calories per gram. So we're just going to talk about the basic layout of this graph and not talk about the numbers. So it's okay that they're using calories per gram. But let's start with ice. We go to a deep freeze that has the ice at minus 20 degrees Celsius, and we bring it out into the room. That ice is going to receive energy from the room, and the ice will warm up. The temperature will change as calories or joules are going into the ice. When it reaches the phase change point, 0 Celsius, then the temperature no longer changes. As energy continues to go into the system, the temperature is constant. So what's happening right here at this second dot? Well, now we have all water, and the water receives that energy and does change its temperature, gets up to 100 Celsius, and now the temperature remains constant again while energy is coming in. Steam is being formed, it's vapor, and we have a situation that the temperature remains constant until all the water becomes steam, and then the steam will change temperature if energy continues to go into the system. So these two behaviors on the graph are modeled with two equations. When we're in a single phase, when it's all solid or when it's all liquid, then we can say the energy that goes in is equal to the mass of the object times a number called the specific heat times the change in temperature. And this delta T, again, you can use degrees Celsius as common. But C is different for water or copper or lead or what have you. There's a table in our online textbook, OpenStax College, that has specific heats for various materials. Water, just to give you a feel for the numbers here, water is 4,186 joules per kilogram for its specific heat. So if we had 1 kilogram of water and we wanted to have the temperature rise by 1 degree Celsius, so 1 kilogram of water, specific heat 4186 joules per kilogram, and we have 1 degree Celsius is our desired temperature change, then what do we have for the Q number? The Q number will be 4,186 joules. And I just realized here, this specific heat number needs to have degrees Celsius in the denominator as a unit. So be careful of that. This is joules per kilogram per degree Celsius. So we put that number in here. The kilograms cancel off, the degrees Celsius cancel off. We're left with joules for our unit. But Q equals mc delta T. This applies as long as we're not changing phase. If the temperature change crosses a boundary, so if we had, right here, if we had ice and then later we have water, then you must do the calculation twice. The specific heat for ice is different than the specific heat of water, and you'll have to account for the energy required to melt the ice. So be careful that the temperature values of start and end don't cross a phase change boundary. There's a different technique for solving the problems if we cross a phase change boundary in temperature. So the phase change is handled this way with energy. The energy is equal to the mass of the object times the latent heat, and these units are correct. So for water, in order to melt ice and create water, we have to add 334,000 joules to a kilogram. 334,000 joules for a kilogram. That's kilojoules here, 1,000 joules. If we're going to change the water into a vapor to steam, it takes 2,260 kilojoules per kilogram. So if you take a look at that, there's a factor of 1,000 is kilo. That's 2,260,000 joules per kilogram. It takes a lot more energy to go into the steam phase from water than to go in the liquid phase from a solid. And again, just look up these numbers when you need them to use them. But we have a situation where we can relate how much energy goes in or comes out of the object to the temperature change, as long as we know the mass and we know the specific heat number. We know what material we're working with. For phase changes, it's a simpler calculation. The temperature is constant. So why is there no delta T factor here? Well, if we multiply by delta T in this formula, that's a 0, and that would be 0 cubed. There is no delta T for the phase change calculation. It's how much mass you have and what the latent heat number. Latent meaning kind of hidden heat, in that as the energy goes in or comes out, there's no temperature change. There's no recording difference on your thermometer as the phase is changing. It's a latent heat, it's a hidden heat. Now some examples of phase change: water vapor in the air, summertime, July, August, lots of humidity, and the cool glass cools down the air nearby. When the air cools down, it loses its ability to retain water vapor, so we get condensation on the glass. Or ice forming on trees. When we go from the vapor state to the liquid state, or from the liquid state to the solid state, energy is released. Just the vice versa. We have to put energy in to the system to go from solid to liquid, or put energy in to go from liquid to vapor. But when we're going the opposite direction, when water condenses, or when vapor condenses into water, or the water condenses into ice, energy is released. So, as the graphic says here, it's a way of protecting the plants, to actually spray liquid water on them and let them receive the energy from the latent heat. So let's go a little further here. Dry ice, and there's water vapor that's condensing to form here. That's it's not the carbon dioxide that's visible. And frost forming, and that's where we actually are going to stop. So these phase changes are interesting, and latent heat calculations are used. When energy goes in and we're in a single phase, then we can calculate the change in temperature for our system. So keep reading and asking questions with that, and I'm sure that you'll have some fun here with calculations that involve energy, change in temperature, or energy and change in phase.